Hello everybody, welcome to our very first video for the semester. This is a review on 6.1. So I'm gonna stick to just a section per video at most, just because I don't want to overwhelm you with too much information in one video. And the way it's gonna work is this is just gonna be like the review that we did in class before, where I would talk about material that's relevant to the quiz, and then so you in this case, you will watch this and then you'll go ahead and take the quiz. The quiz requires a password, and I will provide that password to you during the next video. But the idea is you're supposed to watch both videos because the quiz is on section 6.1 and 6.2. You will have a window of 2 hours to complete the quiz. And that 2 hour window will start an hour before your recitation, and you will have 30 minutes to complete the quiz, and you will only have one attempt at completing the quiz. So for example, if you are on Tuesday, your recitation is on Tuesday at 11, then you will be able to start taking the quiz at 10 o'clock a.m. and you'll have 30 minutes to do it. If you have any questions, any issues, let me know. Let's get started. Alright, so we'll start with section 6.1. And so I've made slides very similar to the ones that Dr. Thunder is using in lecture, and I'll be able to write on the slides here, see? Make comments, we'll go over a few examples and so on. So this is gonna be great. Let's get started. Alright, so looking at the first slide here. Alright, of course, that smiley face shows up on this one too. Let me get rid of that. Alright, so let's just review some basic terms. Right, so we know a set is a well-defined collection of objects, and the idea is, for the sake of this class, we'll just say that well-defined just means that if I give you an object of this set, is there a way you can determine whether or not it belongs to the set? So for example, if the set is everybody, every student, in finite math, if I give you a name of someone who is in finite math, you should be able to tell me that that student, right, the name of that student belongs to the set of students in finite math, and so on, right? And then the objects in the collection are called elements. Alright, so these are the members of the collection, the members of the set, they're called elements, and we usually use the convention that if we use lowercase letters, that's for elements, and uppercase letters is for sets. Of course, this is assuming that the elements of the set are actual letters, right? They could be numbers, they could be anything else. And then the very last bullet point there says that symbol right there just means is in, or is an element of, or belongs to. All those things mean the same thing, right? And then if you put a bar through it, it means is not an element of, right? So this is the negation of the previous symbol, is not an element of, is not in the set, does not belong to, and so on, right? So let's go ahead and just look at a quick example here, right? Just to remind ourselves, what sets are, what elements of a set, what elements are not in the set, and so on. So a very quick example over here. All right, so let's say that T, right? So T, we will use a capital T for the name of the set of letters in my last name, right? So, I mean, if I were to write out the entire thing, it would be this. Oops. Erase that. All right. And then that. Right? But remember that whenever you're writing down the elements of a set, you do not need to repeat any members or any elements of the set. So this set would reduce down to M, U, T, E, and K. Right? So you'd say the name of the set is T, right? And that M, U, T, once I can write it down. So M, U, T, E, and K are the elements, right? So elements of T. And T is the name of the set, right? So you can go ahead and say, of course, M, you'll use a symbol, is an element of capital T. We know that little t is an element of capital T, right, etc. And we can write this for all of M, U, T, E, and K. These are all elements of T. But of course, if I give you the letter A, you'd say A is not an element of T. All right, and anything else that's anything beside M, U, T, E, and K would be not an element of the set capital T. All right. Okay. So that's really all there is to say about sets and elements. Let's go to the next slide. All right, so quickly get rid of all of this mess. All right. This is just like a dry erase board, except the slides here are the background. Okay, so alright, so first bullet point there says two sets A and B are equal if they contain exactly the same elements, right? Pretty straightforward. They have the same number of elements and all the elements are the same. And then today Dr. Thunder clarified this, but worth mentioning that if you use that notation with the bar underneath it, that means a subset of or contained in is contained in. So A is a subset of B means that every element of A is an element of B. And then if you don't use the bar underneath, you say that this is a proper subset of, right? So A is a proper subset of B means that every element of A is an element of B, and there exists at least one element in B not contained in A, right? So in other words, it just usually means that A is strictly smaller than B, right? So let's look at an example or two over here. Okay, so over here, so let's say for example, if A is the sets 3, 4, 5, and let's say B is the set 3, 4, 6, 5. Alright, then as a picture you could say, alright, so suppose this is A, you'd put your 3, your 4, and your 5. Right, so that means that B would be that. Right, so here we can see that there exists at least one element of B that's not contained in A, so we can say that A is a proper subset of B. But it's also okay for you to say that A is a subset of B, right? So both of these are true in that case, right? So conversely, now let's switch some things up, change a few things. So now, so for example, what if A is 3, 4, 5, and then B is now 5, 3, 4? Well, hopefully you can see that in this case, A is exactly the same as B, right? The elements are just in a different order, but these are the same sets, right? So as a picture, this will be A, but it'll also be B. And then, of course, 3, 4, 5 are both, right, are all in both sets, right? In which case you would say that A is a subset of B, but you wouldn't say that A is a proper subset of B, right? So this would not be true, but this would be true. So that will be the difference between the two cases, right? All right, so some other facts. We know that the sets 3, 5, so the set containing 3 and 5 is a subset of B, right? The set 4 is a subset of A, or B, doesn't matter in this case, right? But, so then what you want to keep in mind is, so that subsets by definition are sets themselves, right? So whenever you talk about a subset, it needs to itself be a set. So for example, I can write that the set containing 4 is a subset of A, but I cannot write that 4 is a subset of A, right? Because 4 is not a set, right? So on the left over here, you have the set containing 4, so that's a set, and it's a subset of A, but 4, this is not true. 4 would not be a subset of A. But 4, because 4 is contained in A, 4 would be an element of A. Right, so that's kind of the difference, and this is what 6.1 problem 2b is referring to, knowing the difference between what an element of a set is and what a subset of a set is. Right, make sure you know the difference, very important. The quiz will definitely ask you about that. Right, so that's sets, subsets, elements. So let's move on to the next thing. So next slide, so to speak. Alright, so again, getting rid of all of this. Let's erase all this. Okay, so a very special set is the empty set. We've talked about that one. The empty set is just a set containing, well, absolutely nothing. It is empty, right? The set has 0 elements, nothing at all. Alright, so we know that the set containing nothing, the empty set, is a subset of every set. And then on the opposite end, we have the universal set, which contains everything, right? So empty set contains nothing, universal set contains everything. And that's a set of all elements of interest in a particular problem. So different problem means different universal set, right? And I mean, that's pretty obvious, hopefully. Alright, so next bullet point here is the union of two sets, so A union B, and I'm using this builder notation here because it comes up a lot, so let's get used to using it. So this is just saying that we're looking at all the elements X such that X is in A or X is in B or both, right? So union means or, but when we say or here, what we really mean is and or. Right, so A or B just means it's either in A, or it's in B, or it's in both, right? So that's what union means. And then the intersection, A intersect B, just means all the elements that are both in A and B at the same time. And then finally, A complement just means that we're looking at all the elements that are in the universal set and not in A. Right, so for pictures, let's see, so we have the empty set. You can write it down as this, right? It's a set that contains absolutely nothing. So picture empty set, it's got nothing. Okay, all right, so now remember that this is what number 3, 3a in 6.1 is referring to. Well, it's like there's a difference between empty sets, and what if you had this over here? Well, that's not the same thing, right? Because this is a set that contains the empty sets, right? So as a picture, so if, let's say we call this A, for example. As a picture, the set A here would contain the empty set as an element. So there's a difference between just using the empty set and then using the curly brace with the empty set inside of them, right? So not the same thing. And then finally, if you have a set, let's say the set B is just a set 0, well, that means as a picture, B is right here, and 0 is an element. So also different. So empty set versus a set A here versus a set B here, all different sets. Just keep that in mind. Okay. And then, all right, I need more space. So let's see. We'll say yes. New page. All right, so we know that if we have our universal set U, a set A here, a set B, then A or B is everything here, right? And then another set U. So let's say I'm talking about A and B. So here in this, you'd say A union B, or A or B. In this case, I want to do A intersects B. We know that's everything in A and everything in B at the same time. So that's that middle part right there. And then if we're looking at A complement, sorry. So A complement, and we'll have a set A, for example, here. that would be everything that happens to be inside the rectangular box but outside of A. Alright, so that would be the complement. And then we have our very last slide over here. So let me again erase all of this. So these are just some properties of some of these sets we've talked about. So we can see here that the complement of the universal set is the empty set. Universal set has everything. So what's the complement of everything? Well, it's nothing. And then the complement of the empty set is the universal set. It's like saying, what is the complement of nothing? Well, it's everything. And then if you take the union of a set and its complements, you get the whole universal set. If you take the intersection of the set and its complement, it's nothing, right? Like the complement has nothing that's in the original set. And then these are the Morgan's laws. So these two right here are gonna be, these over here are gonna be useful for certain questions, but it's not necessary that you know them in order to answer the questions on the homework or on the quiz. But they may come in handy to simplify certain other things, right? So now I'm gonna do a bunch of examples using union, complement, and intersection. But because this video is kind of starting to run longer, I'm gonna do another separate video to go over those examples before I get into 6.2. Alright, so I will stop here for this current video and I will pick up in the next one.